inside the atom. Atoms are made of smaller parts. J.J. Thomson, in 1856 to 1940, English physicist, researched the idea that atoms might be made from a combination of particles. He experimented with electric currents in glass tubes called a cathode ray tube, so as such. So we're going to show you guys a simpler version of the diagram to kind of exemplify how he decided to take something like we've seen in the previous lesson, right? We had H2O, and we knew a compound like water can be broken down into atoms of hydrogen and into atoms of oxygen, right? In reality, it's really H2O2, but don't worry about that. Okay, for my class, don't worry about that right now. But that's the way when it's broken down. I'll explain it to you guys when we get to that unit. But water molecules are actually broken down into those two gases, right? And that's how each form. So what he wanted to do was look at each atom and see what else is there to it. What else is it made up of? And that's ultimately what today's lesson is going to be on. Using the tubes, he was able to cause non-radioactive atoms to produce streams of negatively charged particles, which he later named as electrons. So he was able to shoot out through his cathode ray something that this current that was considered made up of negative particles. Now, electrons are negatively charged particles in atoms. With all elements Thomson tested in his cathode ray tube, he noticed that they all produced these electrons. So what did he eventually come up with was that all atoms are made up of electrons. So every single atom must have an electron, because he noticed that there was this stream of a current that was flowing through the cathode ray regardless of which element he used. So in 1897, Thomson proposed that each atom was composed of smaller particles. So let's look at that circle, let's say, that we looked at. He found out that each atom, okay, each element, had these negatives. So he looked at it in terms of this circle that had a whole bunch of these negative charges within it, and with every negative charge he had these positive charges. Thomson noticed that if atoms contain negatively charged electrons, how do they not show a charge? So he had these negatives, and he goes, okay, each one of these atoms have these negative charges. But I haven't really noticed that there's a charge associated to each one of these atoms. So how can you have a whole bunch of these negatives and show no charge? So what he did he pretty much kind of come up with, he must said that there must be positives, the same number of positives associated with it. So if you look at it in terms of charges, right? If you have one negative and one positive charge, you know they're going to show no charge. You have another negative and positive together, they're going to show no charge, right? So all of a sudden, all these charges canceled out. But we knew that there were negatives, right? We knew there were electrons. We knew that there was a negative component, negative particles with it. But they showed no charge, right? So his reasoning, meaning that there must be positive charges that are actually associated. So that's why, well, he noticed that there were negatives, and that's why he drew positives, because he drew the same number of positives as he has negatives, because it showed no charge. Thomson's model shows that the atom has positive sphere with negative electrons scattered throughout it. So the atom itself was positively charged, and within it, he said there were these negatives that must have been circling within, right? And this was what Thomson proposed. So this is Thomson's idea of the atom. Discovery of the atomic nucleus. Another scientist, Ernest Rutherford, he tested Thomson's model of the atom. He conducted an experiment in which he shot positively charged particles at a very thin foil of pure gold. Rutherford obtained the stream of positive particles from a radioactive substance which he placed in a lead block with a tiny hole in it. Okay, so what he did was he decided to shoot, okay, with these particles, okay, which we call the gold foil experiment. And we're going to see a short little video that you can find online. You can find on YouTube, and you can find at the website that I've posted. Out of the hole escaped a stream of these particles, which Rutherford directed at the gold foil. So he shot this gold foil. It went through the opening, but he noticed that there was something else that happened. So during Rutherford's experiment, most of the high-speed positive particles went right through the foil. Right? So we said, well, if we shoot this current through, right, it should all pass through, you know, this gold foil. But what we noticed was there was something else that happened. There was a redirection of some of that stream, and we're going to see that in the following video, which is courtesy of the following website, prenhall.com. You can also find this on YouTube, and it's Rutherford's experiment, the nuclear atom.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So what we have here is we've got these particles. So these particles were being shot in this direction, right? So these are the positive particles. So what happened was, this is the gold foil itself. So he shot them, and it was assumed that these particles were going to go all the way through, as some of these did. Right? But what he noticed, that pretty much, as it was hypothesized, that 1 in about 10,000 of these particles actually bounced either, you know, in a different direction or bounced backwards. Right? So what happened is something in this gold foil deflected these positive particles, right? And so that's where he deciphered, well, there's got to be something else in these atoms that is causing that. There must be something that is causing it to hit, to cause these positive particles to be deflected either backwards or in a different direction that he saw within the gold foil. Rutherford had discovered the nucleus, okay, which is at the center of the atom. That's what deflected these particles. Right? It was something in the nucleus. The nucleus had some kind of mass that allowed it to cause these particles to deflect. So this tiny positively charged part of the atom also contained most of the atom's mass. Now, keep in mind with that gold foil, right? With the nucleus, right, we were shooting positive particles. These positive particles deflected. Now, we knew that the nucleus could not be negatively charged, because if it was negatively charged, the minute the positively charged particle approached the negative, it would have been attracted to it. So we know that there must have been a common charge found within that nucleus that would cause it to deflect in a different direction. So, Rutherford predicted that if nothing blocked the way of the high-speed particles shot at a piece of gold foil, then all the particles would pass through the foil. So this was his prediction. So his prediction was, let me pass through these particles, here's my gold foil, they're all going to pass through. That was his prediction. But what he noticed, right, so here's the evidence. He noticed that some were deflected, some bounced back, right? So that was his evidence. Right? That was his evidence. So the data showed that something massive blocked a few of the particles. So these particles must have been. So what he deciphered was this new model saying that there must be some kind of a nucleus found within the atoms of the gold. Right? So Rutherford revised the atomic model to include a nucleus. So now we have a nucleus associated to the atom. Nucleus is very tiny, but constitutes the greatest portion of mass that the atom contains. Okay? So he shoots these positive particles. Some get deflected backwards, some in opposite directions. But there's something that is pretty much getting in the way of it being just shot right through. So some make it through, right? Because they made it through the opening. But the parts that get deflected, there must be something, some kind of greater mass that is getting in the way. So, reasoning from the gold foil experiment. Question: how could the foil repel the dense, strongly positive alpha particles so dramatically? So the answer that he had, the atom in the foil must possess something that is very dense and intensely positive, right? Because if we're shooting a positive particle, right, the particle is positive, for it to be reflected, so for something to get in the way of it, to cause it to either deflect backwards or forwards in a different direction, right? If it's positive, it also had to be positive. Because if it was negative, the particles would shoot there and all get attracted towards it. So, but the dense positive, something must be relatively small. Now, why? Because the foil let most of the positive alpha particles to go straight through it. So most of them actually went through it. Okay? They were neither repelled nor they were attracted. So even this theory of the positive, kind of, well, we're still iffy about. Right? So, what did we discover? That the atom must also possess a relatively large region that is mostly empty space. So there must have been a lot of empty space still within it. So even this idea, still kind of left question, but we'll realize that there are actually positive particles that are associated within the nucleus. And we'll discover that in a moment. Now, using his gold foil experiment, Rutherford revised the atomic model using his prediction that all atoms everywhere contain a nucleus. So regardless of the atom, right, they all contained a nucleus. We've already discovered the electron. We know that there is a nucleus. We know there are protons. We know that there are positively charges associated to each atom. Right? So similar to Thomson's experiment, except that all atoms, positive charge, and most of the atom's mass were concentrated in this tiny point at the center of the atom. So the mass of the entire atom lies in this nucleus. It's tiny, but it's very dense. Densest part of an atom. So here we have Thomson's model, right? A positive particle with a whole bunch of negatives surrounding it, right? To give it no charge, because he noticed, well, there's no charge associated with it. Now, electrons surrounded the nucleus and filled up most of the atom's volume. However, the atom's total mass is made up within the nucleus. So, all of a sudden we've got Thomson's model and we've got Rutherford's model. Note the difference. Rutherford's model says all the protons lie in the nucleus part of the atom. What's surrounding it are these electrons. So all the positive charges are found in the nucleus of the atom. The electrons circle around this nucleus in a cloud around the nucleus. So that is Rutherford's model. Inside the nucleus, now we've got James Chadwick. Okay? One of Rutherford's students discovered that the nucleus contains neutral particles as well as positively charged particles. The neutral particles in the nucleus of the atom are called neutrons. Right? So these are the ones that actually carry no charge. The positively charged particles in the atom were given the name of proton. So we're looking at pretty much the name of the proton, the name of the neutron, the name of the electron. And these are all the so-called subatomic particles that make up an atom. So each neutron in an atom has about the same mass as each proton in the same atom, but the neutron carries no electric charge. So, neutron, okay, no charge. And we're going to see this again. Proton, positive charge. And we looked earlier at the electron, and the electron had a negative charge to it. So, electrons exist in energy levels, and that's what we're going to see now with the following scientists, or this Danish physicist, who further studied Rutherford's model, the Thomson model, right? And pretty much now we're going to be looking at now a new discovery. So this Danish physicist, Niels Bohr, studied the properties of electrons in atoms and transformed Rutherford's model into the following simplified version that we have. This is what we call the Bohr diagram. Right? And in the Bohr diagram, we show the nucleus of the atom, and surrounding it are these energy levels, or we're going to call them shells. Okay? We're going to call these shells, or orbitals. When you further continue with your chemistry studies, you're going to notice that we've not really shown them properly. But when you see them drawn like this, we're referring to these as either Bohr diagrams, as we have here, or we're going to look at later at the Bohr-Rutherford diagram. So we're looking at it at a non-quantum, level. Okay, so for those who are watching this lesson that are in the senior levels of chemistry, this is based on the simplified Bohr and Bohr-Rutherford models. So, in the Bohr diagram, we have our nucleus and the electrons surrounded, and they're drawn in the same way. So we're going to notice that there are 2 electrons that are going to float around in the first orbital, or first shell, 8 pairs of electrons that are going to circle around in the second shell, or second energy level, and then we can fit another 8 electrons in this third, but we're only showing the actual magnesium atom. And we're going to talk more about Bohr and Bohr-Rutherford diagrams in later chapters. But this is his reasoning. Remember what we said before? The Rutherford model, right? Here's the atom, and in the nucleus of the atom are the positives, right? That's where the nucleus is. And surrounding it were the negatives. Now, Bohr kind of put these energy levels, or these shells, or these orbitals into play when showing his version of the atom. So Bohr suggested that electrons surround the nucleus in specific energy levels that are called shells. He discovered that electrons jump between these shells by gaining or losing electrons. So what happens is a shell can fit a certain number of electrons. Once it is full, it is at a happy state. If it's not full, it's at a so-called unhappy state. Right? It wants to be full. Right? It wants to be supposedly stable. And we'll talk about that also in a later chapter. So each shell can contain only a specific number of electrons. So what you're going to see in some of the worksheets that I'm going to provide for you, your drawings of the diagrams are going to be as such. So what we have here in the center is our nucleus. Circling around it, we've got 1, 2, 3, 4 orbitals, or 4 shells. Okay, we're going to refer to them as shells or orbitals. And these are the electrons. And what we're going to do is you're going to see a diagram like this, and what you're going to do is you're just going to color in the correct number of electrons that are going to show of that atom. So in the nucleus, right, we've already discovered that there are protons, positive charges, and there are no charges, neutral charges. And we're going to talk about that also in a later chapter. The maximum number of electrons that can exist in each of the first 3 shells. I've shown you 4 shells. We're going to ignore this last shell for now. So look at the first 3 shells. The first shell, right, just surrounding the nucleus, can only contain 2 electrons. The next shell, the second one, can fit a maximum of 8. The third shell can also fit 8. If you look at the periodic table, look at the first row of the periodic table. How many atoms are there? There are 2. Look at the second row of the periodic table. How many atoms are there? There are 8. Look at the third row. What are the number of atoms that are across it? Also another 8. And we're only going to look at really the first 3 rows, and we're actually going to look at the 2 atoms in the 4th row, and we call them rows, but you're going to find out in a later chapter that they're in fact called periods. And we're actually, the only ones in period number 4 or row number 4 that we're going to look at is potassium and calcium. Those are the only 2 atoms that we're actually going to look at in the 4th period, okay, or the 4th row for these rules. So we're only going to draw a maximum of 2 more electrons when we use this 4th shell, right? If we're drawing Bohr or Bohr-Rutherford diagrams of potassium and calcium. So here we have the periodic table, right? So as we said, right, first row, 1, 2 atoms. Here's the second row, 2 here, plus another 6 there to give us the total of 8. The third row, again, 2 here, plus another 6 here, also to give us 8. And as I said, we're only going to look at potassium and calcium. Okay, so you are, for this grade 9 course, you guys are responsible for the first 20 to be able to draw these type of diagrams. And we're going to talk about these as we get to that part of the chapter. Many people still use this model to describe the particles that make up the atom. So this is what we're going to call as the Bohr and Bohr-Rutherford diagram. So when we use this way of drawing an atom, right, this is the simplified version, this is the grade 9, grade 10 version of the atom. Once you get into the senior levels of chemistry, we're going to look at pretty much all of these and how they're drawn. And we don't really use this kind of drawing anyway for that level. So here is what we're talking about in terms of the senior level. The quantum mechanical model, the most advanced and accurate model of the atom, and the one in use today by physicists and chemists, is called the quantum mechanical model. Electrons do not exist as tiny points inside an atom. Okay? In fact, electrons exist in specific energy levels, but they surround the positively charged nucleus in a form resembling a cloud. So, in fact, the nucleus is really this tiny part. And this huge cloud surrounding it are where the electrons are found. Okay? And what you're going to see, like I said, in the senior level, we're going to be looking at things like s orbitals, p orbitals, d orbitals, and f orbitals. But don't worry about that for my grade 9s and grade 10s. We won't see that until the senior levels. A summary of the atom. So all elements are composed of atoms, and one atom is the smallest unit of any element. We know that they can go further down into smaller subatomic particles of a proton, electrons, and neutrons. These all make up an atom. Right? But the smallest possible entity that we can actually keep is the size of the atom. Within each atom are smaller particles that are called these subatomic particles. So, the 3 subatomic particles that we said, the proton, the neutron, the electron. So the positive charge, the no charge, and the negative charge. That's what make up, so all three of these together form the atom. Each one of these subatomic particles exhibit different properties. Okay, obvious one is its charge, right? That's the one obvious thing between all of them. Another property is their relative mass. You do not need to memorize these numbers, okay? But just to kind of show you guys just how different each one of these subatomic particles are to one another. Okay, so it compares the mass of an object to the mass of another object. That's really what the relative mass is. Relatively, how, what is its mass compared to another one? Right? So an electron is the least massive subatomic particle of the three subatomic particles. So what we're going to do is we're going to give it a relative mass of 1. Right? So we're going to treat it kind of like it's the really, really light subatomic particle. Right? The heavier subatomic particles are actually the protons and the neutrons. So when you look at the atomic mass of an atom, right? So that's the bigger number. So if you look at the periodic table and you see, you're going to see two sets of numbers. One set of numbers that are called the atomic number are the numbers that go in order. 1, 2, 3, 4, 5, 6, 7, right to number 118. But the bigger of the two numbers, usually the second number that's shown in all periodic tables, is the atomic mass. So that mass is really made up of protons and neutrons. So 99.9% of the mass is really made up of those two subatomic particles. Proton has a relative mass of 1836. So that means it's 1,836 times heavier than an electron. A neutron is a little bit heavier, but not much. If you look at the comparison, the neutron is 1,837 times heavier than an electron. Right? So when we're looking at such a big number, 1836 to 1 in terms of a mass, right? And 1837 to 1. Really, that 1 here is going to make a difference when we're comparing the proton and the neutron. But keep in mind that the majority of the mass, right, 99.9% of the mass of an atom is made up of protons and neutrons. And we're going to talk about how much of each in a later chapter. So, properties of subatomic particles. So, the proton symbol that we use is a P or a plus sign. Right? Positive. So, relative mass, as we said, 1,836. Numbers that you do not need to memorize. The charge associated is a +1. So, for each proton, each one carries a +1. So, if we have 4 protons, we have 4 positives. Location of the proton, the nucleus. Neutron. Symbol for the neutron, we're going to use the letter N. The relative mass, 1,837. The charge is 0. There is no charge associated to the neutron. So think no neutron, right? So no charge for neutron. Location of the neutron, also the nucleus. All right, so that's what Chadwick identified. The electron, we're going to give the symbol E or a negative, okay, to show the symbol of the electron. The relative mass is 1, very light, the lightest part of the atom. The charge that's associated with the electrons is a -1 charge, and the location of it is in energy levels that are surrounding the nucleus. According to the Bohr and Bohr-Rutherford diagram, they are found in the shells or in the orbitals. Okay, and these are based on the Bohr and Bohr-Rutherford diagrams. Okay, but in any other way, they're really, here's our nucleus, protons and neutrons in it, and all around here are where the electrons actually surround. So, overview of all the atoms. So, John Dalton suggested that all atoms are tiny spheres, and each sphere is slightly bigger to represent each different one, right? So that was the most primitive version of the atom, that each one was in sphere shape. Ultimately, J.J. Thomson said that the particle was positively charged, and because it exhibited no charge whatsoever, it must have had a whole bunch of these negatives within it. That was J.J. Thomson's idea of the atom. Then eventually Rutherford came in and said, wait, these positives are actually enclosed within a nucleus, and surrounding it were these electrons. So notice the difference between Thomson's model and Rutherford's model. Rutherford said, there's got to be a nucleus. That's where the positives are. Remember the gold foil experiment? Positive particles that were shot. Some bounced off this nucleus. Some made its way all the way through. Right? Ultimately, Chadwick said, well, in that nucleus, we've got to have some neutrons. Right? So these no-charge particles that make up part of the mass. Right? So notice here how the atom is evolving. Right? Then Bohr came in and said, well, you know what? These electrons, they're not just randomly around the nucleus. They're actually at certain energy levels. That's what Niels Bohr came up with. And then eventually, in pretty much more scientific, right, at a more quantum level, that this nucleus is at the center with a cloud of electrons that are in certain energy levels, but not drawn the same way that Niels Bohr used to show the size or the actual shape and composition of each atom.